Hello again, class. It's been a while since I've done a video lesson. I hope you've been well. I couldn't find a video that was quite good enough for specific heat capacity, so I wanted to do one myself. Specific heat capacity just basically refers to an object's ability to A, heat up or lose heat quickly or slowly, and B, how much energy it takes for that object to heat up, or how much energy that object releases when it cools off. So if you think about going to the beach, the sand gets really hot fairly quickly, but then you run into the water and the water is cold. That has everything to do with specific heat capacity. Sand has the ability to heat up really fast, but then when you put like an umbrella over top of the sand, and then you put your foot in the sand after the umbrella's been out there for a little bit, the sand is cool again. Whereas the water doesn't have that same ability. So sand has a much lower specific heat capacity than water. So the definition of specific heat capacity from your textbook is that specific heat capacity of a substance is the amount of energy required to increase the temperature of 1 gram, so that's your mass, of a substance by 1 degree Celsius. Which is a little bit confusing, but for every 1 gram to increase 1 degree Celsius, that's how much energy is needed to be input into the system. For example, it'll take 4.19 joules of energy for every 1 gram of water to increase by 1 degree Celsius. Copper, for instance, only takes 0.385 joules to increase 1 gram by 1 degree Celsius. So copper is going to heat up a lot faster. That's why metal gets hot quick, whereas water takes a long time to boil. Now, the other side of the coin for specific heat capacity is when they cool down. The specific heat capacity tells us how much energy is released into the system. So when things cool, that heat is lost to the system, to the environment. So it'll tell you how much energy is released. It's the same number. So this 4.19 joules of energy is released into the system when 1 gram of water cools by 1 degree Celsius. And this is why places like Vancouver don't have the high fluctuations of temperature change. So at nighttime versus the daytime, the temperature doesn't change as much as it does in, say, Calgary. The reason for this is because Vancouver has the ocean right there. So that all that water during the day gets heated up by the sun and it traps all that energy. Then at nighttime it cools off, but as it cools, it releases a bunch of energy into the system. And that warm energy then gets transferred into Vancouver, and Vancouver's temperature stays roughly consistent. Whereas Calgary, during the day, all the surfaces of Calgary heat up quite fast. But then when the sun goes away, all that energy also leaves quite fast. So because most solids or non-water material have a relatively low specific heat capacity, it's going to take a lot less time for it to heat up and cool down. So when the sun rises, you feel that heat right away, and that it warms up the environment fairly quickly. Whereas if we had the ocean right beside us, it would take a little while longer. Alright, so we can use the specific heat capacity to calculate how much energy is released or absorbed in a system. Specific heat capacity has been given the letter C. So whenever you see a C, it's specific heat capacity. And again, it's measured in joules per gram degree Celsius. So per gram and per degree Celsius. It is a constant. We talked about that. And by using this formula, we can find out how much energy is released in the system. This is how much energy, and that's measured in joules. So it's going to be mass times your specific heat capacity times the change in temperature that it experienced. So let's take a look at the unit analysis here. If we have kilograms for the mass times joules per gram degrees Celsius times degrees Celsius, what are we left with? Well, we'd have our grams are going to cancel, but we're still going to have that kilograms, so that's going to be a problem. So instead of having mass in kilograms, we're going to need to have mass in grams. So that's really, really important. Remember how we had mass in kilograms our whole science 10? Well, now we're going to have it in grams. Or we'd have to have this in kilograms, but that's really ugly. The constant is going to be measured in grams. So we're going to change this to be grams. And then if we got rid of the kilograms and made it grams instead, like this, now our grams would cancel. Cancel with this one. Our degrees Celsius is going to cancel, and we're going to be left with joules, which is the proper unit for energy. So let's try an example. 19 kilograms of water heats up from 18 degrees Celsius to 25 degrees Celsius. Is energy released or absorbed by the water? Well, let's think about this logically. I don't want you just to type in the numbers into the equation. If water is going to heat up, that means it's absorbing energy, which means we have to be putting energy into it. So it's being absorbed by the water. That energy goes into that water, and that water holds onto that energy and heats up. Now we have to find out how much energy. So let's do the equation. Q is equal to mc delta T, where our mass is going to be 19,000 grams. Remember, we want it in grams, times the specific heat capacity of water. So you look on your formula sheet, but it's 4.19 joules per gram degrees Celsius. And then we have a change in temperature. So how much temperature has it changed by? Well, remember, delta T is just the change in temperature, which is T2 minus T1. So that's going to be T2 here, and T1, give me 25 degrees Celsius minus 18 degrees Celsius. When we plug that all in, I seem to have lost my calculator. Bear with me. We get 19,000 times 4.19 times 25 minus 18 is 7. You get 557,270 joules, or we need two significant digits, 5.6 times 10 to the power of 1, 2, 3, 4, 5 joules. That's how much energy is absorbed by that water. Alright, let's try another one. So now your water is being cooled. 10 kilogram mass of water is being cooled from 45 degrees Celsius to 10 degrees Celsius. How much energy is released into the atmosphere? So now it's being cooled, so it's going to release energy. So again, Q is equal to mc delta T, which is 10,000 grams times 4.19 joules per gram degree Celsius, times by 45 minus 10 is going to be 35. And now you get 10,000 times 4.19 times 35, 83 million. That's actually going to be negative 145 joules, or 8.3 times 10 to the 7 joules released. So that's a ton of energy being released into the atmosphere, because it's quite a steep drop off in temperature. It's quite warm at 45 degrees Celsius and then drops down to 10 degrees Celsius. It's going to release a ton of energy. Alright, let's do one more. 1000 joules of energy is added to an iron pan, which has that as our specific heat capacity, causing it to heat up from 21 degrees Celsius to 95 degrees Celsius. What is the mass of the iron pan? Well, we're going to do the same steps. Q is equal to mc delta T. So, in this case, it's different because we want to solve for mass. So we're going to have to rearrange the formula. This shouldn't be new to you, but you can just divide by C and T. And you get Q over C delta T is equal to M, which in our case, this is Q, because it's the amount of energy, 1000 joules, divided by our C of 0.499 joules per gram degree Celsius. Remember, this is different because this is for iron and not water. And then underneath is our delta T, which is 74 degrees Celsius. Now, 1000 divided by 0.499 divided by 74. We end up with 29.1 grams, or if we want to have two significant digits, 29 grams. So that's how we do specific heat capacity. If you have any questions, as always, I'm available on Discord. Have a great day.